It feels like AI is moving at a truly blistering pace. Seriously, every few months there's a leap forward that feels like it should have taken a decade. But underneath all that progress, the way these models actually think and process information has gone through this really fascinating evolution, hitting one fundamental wall after another, and then smashing right through them. So, when you type a prompt into an AI, you're tapping into this incredibly complex neural network. But have you ever stopped to wonder how it actually, reads your request? Does it read it like you and I do, one word after another? Or does it just kind of absorb it all at once? The answer has changed dramatically over the years, and that change is the key to everything, both their incredible power and, believe it or not, their hidden limits. Because here's the thing, even the most powerful models we have today eventually hit a wall. It's a memory limit. If you ask an AI to remember the first chapter of a book by the time it gets to the very last page, things start to get, fuzzy. It starts to forget. So, what exactly is this wall? And more importantly, how are we finally starting to tear it down? To get that, we actually have to take a quick trip back in time.
Right. So, to understand where we're going, we first have to see where we've been. Before this whole AI boom really took off, models were basically stuck in a massive processing traffic jam. They had what we call a sequential bottleneck.
The best way to picture it is like this. The older models, which were called recurrent neural networks, or RNNs, were forced to read everything through a tiny keyhole. I mean, they'd process the first word, create a little memory of it, then move to the second word while trying to remember the first, and on and on and on. Imagine trying to understand a story one single word at a time without ever seeing the whole page. It was just incredibly inefficient. And this one-by-one process, it creates a huge problem. The longer the sentence, the more steps it takes, and the higher the chance the model just forgets what it read at the beginning. Because of this built-in sequential nature, you couldn't really train them on massive data sets in parallel. They were just fundamentally and really frustratingly slow. And check this out. This table from a totally game-changing paper in 2017 shows you the problem in plain numbers. For the old way, the recurrent network, the number of steps it takes grows in a straight line with the length of the text. That's what that O of N means. More text, more time. Super simple, but super slow. But then look at the row below it, self-attention. The number of operations is O of 1. That means it takes the exact same amount of time to process 1,000 words as it does to process one. It's constant. This wasn't just a small improvement. This was a complete and total paradigm shift. Okay, so back to 2017, a team of researchers at Google publishes a paper that just completely rewrites the rules. It introduced a new kind of architecture that threw out that slow, sequential processing completely. And the paper's title was just as bold and simple as the idea itself. Attention is all you need. It basically proposed a new model that relied on one single mechanism called attention. And with that, it just tossed the old rulebook right out the window. And this is it. This is the engine behind pretty much every single major AI you use today. It's called the transformer architecture. Now, it might look a little complex, but the core idea is absolutely revolutionary. Instead of that slow, sequential, one word at a time slog, the transformer can look at the entire input, the whole sentence, the whole paragraph, all at the same time. It sees the big picture instantly. The secret sauce that makes all this possible is something called self-attention. Here's a simple way to think about it. For every single word in a sentence, the model calculates an attention score to figure out how relevant every other word is to it. So in a sentence like, the robot picked up the ball because it was heavy, self-attention is what lets the model know with certainty that it refers to the ball and not the robot. It creates this amazing web of connections all at once, so it understands the real context. So let's go back to our first analogy. We've gone from that tiny, frustrating keyhole where the AI could only see one word at a time to just throwing the doors wide open. Now, the AI can see the entire page all at once, and it can understand all the complex relationships between every single word. It was a complete revolution in how AI could comprehend things. But, of course, it's never quite that simple, is it? Solving that sequential problem unlocked an incredible amount of power, but it also created a brand new kind of bottleneck. The transformer's short-term memory, what we call its context window, was still limited. And researchers have a great name for this problem: context rot. Even with the superpower of seeing a whole page at once, if you try to give the AI a whole book to read, it really starts to struggle. The quality of its answers, its reasoning, it just degrades the more information you try to cram into that context window. It's basically the needle in a haystack problem. The bigger the haystack gets, the harder it is for the AI to find the needle. And this graph shows the problem crystal clear. We're looking at the performance of a top-of-the-line model as the amount of text it has to deal with gets bigger and bigger. Just look at that line. It's a nosedive, a clear, dramatic drop-off. This isn't some minor quirk. It's a fundamental limitation that even the very best models today suffer from. Which, of course, brings us to the next great challenge. If just stuffing everything into the model's memory doesn't work for these truly massive contexts, we're talking an entire novel, a huge financial report, or a whole software repository, then what on earth is the solution? Well, the answer required a completely different way of thinking. Instead of trying to build a bigger and bigger memory box for the AI, a new approach says, hey, what if we treat that massive amount of information not as something to be memorized, but as an external environment to be explored? And this changes our whole analogy. We're no longer trying to force the AI to memorize the entire library. I mean, that's impossible. Instead, we're teaching the AI how to be a brilliant researcher inside that library. We're giving it the ability to walk the aisles, pull specific books off the shelf, and read just the pages it needs to answer our question. This new architecture is called a Recursive Language Model, or RLM, and here's the absolutely brilliant part. That long prompt, our entire library of information, isn't crammed into the AI's short-term memory at all. Instead, it's just treated like an external file. The AI can then write its own simple code to search and navigate that file. And here's the recursive trick. When it finds a passage that seems relevant, it can call on a smaller, focused version of itself to just analyze that one snippet. It's basically delegating the work, piece by piece. And here's what that actually looks like in practice. I mean, this is so cool. You can literally see the RLM writing Python code on the fly. It's defining functions to find keywords, it's splitting this massive text into manageable chunks, and then it's launching these tiny, focused queries. It's not just reading anymore, it's actively strategizing. It's breaking down a massive problem into bite-sized pieces that it knows it can solve. And here is the incredible result of all that. On the left, you see the base model's performance just collapsing as the context gets longer. That's our context rot. But on the right, the recursive language model's performance stays almost perfectly flat, even as the input scales up to 1 million words and beyond. It hasn't just managed context rot, it has, for all intents and purposes, completely solved it. So, what does all of this mean? We've gotten quite a journey here, right? From the slow, sequential bottleneck of early AI to the parallel processing revolution of the transformer, which then hit its own memory limit, and now to this amazing recursive solution that turns that limit into an interactive environment. You can really think of it as an evolution in 3 acts. We went from reading through a keyhole, one word at a time, to seeing the whole page at once, to now having an intelligent researcher that can access an entire library. Each step is just a fundamental shift in how AI can reason about the world. So why does this matter so much? It means AI can now be applied to problems on a completely different scale. I'm talking about analyzing the themes across an entire series of novels, debugging millions of lines of code, or doing deep research across thousands of medical documents. These things are no longer science fiction. And this incredible leap forward opens up a final, really tantalizing question. When an AI no longer has a meaningful memory limit, when it can effectively reason over a body of information as large as we can possibly give it, what are the new limits? What new problems will that create, and what new revolutions will we need to solve them?